Yesterday we spent some time looking at position time graphs. Remember, the position is always on the y-axis and time is always on the x-axis. Time is which variable? The manipulated or the responding variable? Which variable is it that always goes on the x-axis? Manipulated or responding variable, right? Yeah, good. It's the manipulated variable that always goes on the x-axis. So time would be the manipulated, position would be the responding. Sometimes we see a graph that's as simple as this, where we have a straight line that goes through the origin there. Sometimes we have a line that, that looks like this. It's also a straight line, but maybe doesn't go through the origin. Or then sometimes maybe we have a situation like this where we've got a couple of different lines. One that is sloping upwards and then one that's flat or whatever the case may be. It's not a big deal. Okay, if we have two different shapes on the graph, then we just treat it as two separate stages and look at each stage individually. There's a bunch of things that we can find from this graph. Okay, the first thing is position. Whenever we want to find position, that's an easy question, right? Whenever we get position, all we do is go up and over. Anytime you want to find something that's on one of the axes of a graph, then you're just going to read it straight off the graph. So if I want to find the position at, let's say, 1 second, then I'm going to go up and over, and I'm going to read the position right there. If I want to find the position at, say, 3 seconds, I'm going to go up and over, and I'm going to read it right there. So position is pretty easy to find. All we're going to do is go up and over every single time. Now, the second thing that we had to find on graphs was displacement. Displacement, you remember, is delta D. It's the change in position. If I can find a position, then I can find two positions. And if I can find two positions, I can probably subtract them. And if I can subtract them, then I can find displacement. So for position, you're going to go up and over. For displacement, you're going to get position twice, and then you're going to subtract the two numbers, df minus di. Is that good? The next one, that's the toughest one, the velocity. The velocity. Does anybody remember how to find the velocity on a position time graph? What is it? It's the slope of the graph. Now, this is two shapes, right? This is a straight line that's sloping upwards and a straight line that's horizontal. We're not going to find probably the velocity of the entire thing, although we could. I think once, actually, in your worksheet, it asks you to do that. Most times, it asks you to find the velocity of this stage or of this stage. Okay, you want to find the slope of the first stage? We're going to say rise over run, or y2 minus y1 over x2 minus x1. Pick any points you want. Probably the beginning and the end. y2 minus y1. x2 minus x1. Get a value for the average speed there. Finally, I asked you yesterday to find the instantaneous velocity, the velocity at a specific moment in time. What if I asked you to find the velocity right here? What if the velocity here was 12 meters per second? What's the instantaneous velocity right here at, let's say, 1.3 seconds? What's we going to do to get the instantaneous velocity at this moment in time? Yep. It's the same as this, right? If the velocity is 12 meters per second everywhere along that line, then the velocity at that spot on the line must be 12 meters per second. All right, we had 3 questions to do for homework. We're going to go through all 3 of those right now in preparation for our quiz on this tomorrow. We're going to go through them pretty quickly. Stop me if you need to spend a little bit more time on it. I'm going to go through them and ask you what you got as answers, and then we'll check those to make sure that they're right. What's the position at 7 seconds here? How do you find position? It's on the y-axis, right? If you're looking for a variable that's on one of the axes, you're just going to read it straight off the graph. Let's go up and over. At 7 seconds, we go up and over. The position is 30 meters. We should really say 30 meters. That's it, actually. Thought we had a direction given to us there. We don't, so that's all we can say, 30 meters. How many people got that one? Okay, good. You will be asked that tomorrow. What's the displacement between 0 and 5 seconds? Well, displacement is the final position minus the initial position. The position at 5 seconds up and over is 30 meters. The position at 0 seconds is 0 meters. So 30 minus 0 meters gives me 30 meters. So position indicates where I am. Okay, and question 1A, I am at 30 meters at 7 seconds. Displacement represents how far I've gone, the change in position. I've gone 30 meters during stage A, between 0 and 5 seconds. What's the average velocity between 0 and 5 seconds? How do you find that? We just reviewed this, right? Somebody just whispered it over here. How do you find the velocity between 0 and 5 seconds? Starts with an S. Find the slope. Somebody said it, find the slope. So let's say V is equal to y2 minus y1 over x2 minus x1. y2 is going to be 30 meters. y1 is going to be 0. So it's going to be 30 minus 0 over 5 minus 0. That's going to give me 6.0 meters per second. How many people got that? 6. Good. Again, it's going to be on your quiz tomorrow. The average velocity between 0 and 9 seconds. This one's a tougher one. Between 0 and 9 seconds. It's 2 lines. How do you find the average velocity when you've got 2 lines? Anybody think they have that? Who thinks they have the answer to that one? What'd you get? Okay. Yeah. Close, total displacement over the total time. Right? Velocity is displacement over time. Displacement is, in this case, 30 meters. Okay, we've gone from 0 to 30 meters. The displacement is 30. The total time is 9 seconds. So that's going to be 3.33, I think. Anybody get that? Good. I knew there was people that had the answer that just wouldn't raise their hands when I said how many people think they got it. 3.33 meters per second. What's the instantaneous velocity now at 3 seconds? How fast is this object moving right here? We need a quick answer for this one. It's not rocket science. The velocity over the entire stage A is 6 meters per second. What's the velocity at any point along that stage? 6 meters per second. And find out the instantaneous velocity at 8 seconds, right here. What do you know about an object that's represented by a graph that's a flat line like that? It stopped. So what's its velocity at 8 seconds? 0 meters per second. Let's pretend this is a 5-question quiz worth 5 points. How many people got 100 on that quiz? Good. Then you should get 100 on tomorrow's quiz. Okay, how many people got an 80, 4 to 5 on it? Okay, we won't go any lower than that. We won't poll the people that got a 20 or something like that. Okay, let's do another one here now. The displacement between 0 and 10. Displacement between 0 and 10. Remember, displacement is change in position, df minus di. We can find positions. The final position at 10 seconds is 0, right? 0 meters. The initial position is 14 meters. 0 minus 14 is neg 14 meters. Between 10 and 18? Well, between 10 and 18, we're going from 0 to 6. So we're going to say it's 6 minus 0 is 6 meters. The average velocity between 0 and 10. Velocity of the slope, y2 minus y1 over x2 minus x1. Between 0 and 10, the final position is 0. The initial position is 14 over a time of 10 seconds. Gives me negative 1.4. Who got that one? Negative 1.4 meters per second. Good. Who said negative? Who said positive? Anybody say positive 1.4? Yeah. Okay, just be careful about that. And that's a really, really easy mistake to make. We've all made it, and we'll probably all make it again. Just be conscious of it. If it's sloping downward, final minus initial, the final is lower than the initial, so it's got to end up being a negative value. Now what do we got? The average velocity between 10 and 18 seconds. the average velocity between 10 and 18. Well, we're going to do the same thing, y2 minus y1 over x2 minus x1. This time it's 6 minus 0 over 18 minus 10. We get 6 over 8, which is 0.75 meters per second. Positive or negative? It's sloping upwards, so it's going to be a positive value, right? The final value is bigger than the initial. And finally, the average value of the velocity between 0 and 18. This is going to go back to displacement over time again, like we had in the last question. The displacement between 0 and 18, well, the final position is 6. The initial was 14. The total time is 18 seconds. So we've got negative 8 over 18, which I believe is negative 0.44. Is that right? Who got a 5 out of 5 on this one? Pretty much the same people, I think. It's not a big surprise, I guess. Who thinks they could get a 5 out of 5 on this one now? One other person? I hope it's more than one other person. Okay, let's take a look at our last one here. The last one that we did, at least. Position at 30 seconds. This one's easier. Position at 30 seconds. Go up and over. Position is 6 meters. Between 0 and 4 seconds. Sorry, between 0 and 45 seconds. It's easier, but sometimes it seems harder. What's the displacement between 0 and 45? What do we know about a straight, flat line graph like this? What's happening to the object? It's... What do we know about it? Stopped, right? It's stopped. It's not moving. And what's its displacement if it's not moving? 0, right? The average velocity between 0 and 45, if it's not moving, it's 0 meters per second. In the instantaneous velocity at 15, if it isn't moving, it's 0 meters per second. So 6, 0, 0, 0. Who got 4 to 4 on that one? Okay, good. Issues with those? You guys feel okay about them? I want to do a quiz tomorrow, but I want to make sure that you got a good fighting chance at getting 100 on that quiz too. It will be not anything different than what we've seen here today. Okay, if you can do these, you're in good shape for the quiz. What I want to do now, today, go a little bit further with position time graphs and plot position time graphs ourselves. Okay, the graphs that you were given on this worksheet and in your practice problems and your example problems were plotted for you, and they were perfect. They were perfect straight lines. There was no real data points. The lines just ended up being just right. Okay, when we have real data, sometimes it doesn't work out that way. Sometimes the data points are kind of scattered a little bit, and we have to interpret those and draw our nice line of best fit and so on. The first thing that I want to recognize when we're plotting these graphs is which column of a table is the manipulated variable. We know which variable goes on the x-axis, which on the y-axis, but how do we translate a table into a graph? Well, we know on the x-axis it's manipulated variable, on the y-axis it's responding, but in a data table, the first column will also be manipulated, and the second column will also be responding. So even if you're not told, what the variables are, if you're told to plot a graph of this and this, you know which one to do on which axis. The first column always goes on the x-axis, second column always goes on the y-axis. So let's replace that now. Let's say on the x-axis we've got time, and that's in seconds, and on the y-axis we've got position, and that's going to be in meters. Well, now we have to create nice even intervals for those variables on each of these axes. Time goes from 0 to 20. Let's go 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. Notice we have not taken up the entire piece of graph paper on the x-axis, but we've taken up most of it. We want to use as much of the graph paper as possible. You got that? As much as possible. Now the y-axis goes from 12 to 102. So let's go 20. No, let's go 10. Use a pencil for this, by the way. Why do I suggest you use a pencil? What if you get to 102 by here? Do you want to stick with that? You want it to be way up here somewhere, right? You want to take up as much of the axis, as much of the graph paper as possible. Let's try this. Let's try 10, I should say. 20, 30, 40, 50, 60, 70, 80, 90, 100. And then we got to go to 110 because we're a little bit over 100 there. Is that good? Have I taken up most of the graph paper? Do I have even intervals on this? 10, 20, 30, 40 instead of 10, 11, 17, 24? I do. Okay, graph looks good so far. We forgot one thing though. Something we should have put in at the very beginning. Anybody think they know what it is? The title. The title of the graph will always be responding versus manipulated. So in this case, it would be position versus time. Make sense? We should, by rights, use a ruler here now to draw in our axes. Now, I can't use a ruler on here, really. I'll try, actually. I'll try drawing a straight line with this function right here. Okay, you should use a ruler to trace over those lines. Yeah, that didn't work out perfect, but it's close. Let's see what we can do there. Move that down. Yeah, that's not bad. Make sense? Start plotting some points here now. Okay, my first coordinate is 2, 12. 2 on the x-axis, 12 on the y-axis. So let's draw that point in. Okay, 2 and 12 is about right here. Okay, we can draw that as an X, we can draw that as a dot, we can draw it as whatever we want, really. My suggestion, please, is to draw it as an X. The reason that I'd like to see it drawn as an X, not mandatory, but I'd like to see it drawn as an X, because I need to see the point. If you draw it as a dot, it's okay, but I better be able to see the point. Okay, if you draw a line right over that dot, it might hide the point. X's, doesn't matter where you draw your line, you're still going to be able to see the point. My next coordinate is 4/4, 18, so it's going to be somewhere around there. 6, 30, right there. 8 and 43, it's going to be about right here. 10 and 49, it's going to take me to right here. 12 and 59, it takes me to here. 14 and 72. 16 and 81, 18 and 88, 20 and 102. I'm not going to do anything with these data points yet. I'm going to give you a chance to copy out these data points and do it yourself. But please stop there if you do have these points plotted. Do not join the points together. Don't do anything with it. I'm going to ask you a question right now that I'll ask you again tomorrow. The answer is never. Okay, that's the answer. It's like Jeopardy here. I'm giving you the answer. The question is, when do you join the points together in physics? What's the answer? Never join the points together in physics. Never join the points together in physics. We'll talk about what we do with these points again in just a couple minutes after you've plotted them yourselves on your graph paper. When you're done plotting all those points, what we want to do now is not connect the dots. We never do that. Okay, that's a grade 1 thing. You connect dots in kindergarten in grade 1. So you form this nice little picture. We don't do that in physics 20 or physics 30. What we do in physics 20 and physics 30 is draw what we call a line of best fit or a curve of best fit if it looks like it should be a curved line. Okay, if we got a straight line or points that are almost a straight line, then we draw a line that approximate those points. We draw it through those points. We don't join the points. We draw a line through those points to approximate what this appears as if it should be, a straight line. So I'm going to draw my line of best fit looking something like this. Okay, again, notice I'm not connecting any points. It may actually touch some points. That's okay. But it's not purposely connecting any points. It may or may not go through the origin. It may or may not touch a particular point. This would be a bad line of best fit if I had drawn that. Why? Doesn't really follow the pattern, right? It goes upwards, it slopes upwards, but not at the same rate. Okay, that first one that I drew is a good line of best fit because it approximates what I actually see. These points look like they should be a straight line that looks pretty much like that. You want to have more or less an equal number of points above the line and below the line, more or less. Once you get to that point where you've drawn all your points, draw your line of best fit. I'll take a walk around, I'll take a peek, and I'll see if your line of best fit is good or whether it should be a little bit steeper or not quite as steep. You guys, good question just asked again. I briefly touched on this earlier, but just kind of in passing. That line of best fit does not need to go through the origin 0, 0. Okay, if it does, that's okay, but it doesn't need to. Okay, I don't want you to force it. I want you to pretend you don't know where the origin is and you don't know where your axes are when you're plotting your line of best fit. Okay, cover them up. Cover up your origin. Cover up both axes and look at just the points. Draw your line of best fit through the points. And if it happens to, by coincidence, go through the origin, then that's great. If it doesn't, that's okay too. So pretend you don't know where it is. Okay, that way you're not going to force it to go through the origin when it really shouldn't go through there. You can see that my line comes pretty darn close to going through the origin, right? It's because of my data, what my data points actually are. But that's only because, only because the data points took it there, not because I was trying to start it there. All right, let's take a look at what comes next. We've got a straight line, or at least we've approximated this graph as a straight line. This is pretty much constant velocity because it's a straight line. Now what we want to do is find the value of that velocity. How do we do that? You guys know this. We talked about this yesterday and earlier today. How do you find the velocity on a straight line graph? Take the slope, right? Slope is equal to y2 minus y1 over x2 minus x1. Rise over run. We can pick 2 points on this graph, doesn't matter where, but do not pick data points. Once you've drawn your graph, your data table is gone forever. Do not pick data points. Pick points on the line. Doesn't matter where you pick them, okay, but preferably far apart. Okay, I'll go these 2 points right here. Okay, those 2 points in red. My y2 is going to be 95. My y1 is 15. My x2, now this is a little bit trickier. My x2 looks to be about 18 point, that's 18, 19, I don't know, about 18.8, 18.8 seconds. My x1 looks to be about, well, this is 2, this is 3, looks to be about 2.6 or so. 95 minus 15 is 80. Over 18.8 minus 2.6 is 16.2. My slope there, which represents my velocity, would be 80 divided by 16.2. That works out to be 4.9. And the units for that would be meters per second because it represents velocity. 4.9 meters per second. Does that make sense? I'm going to give you an assignment in just a moment that you're actually going to hand in to me tomorrow. It's essentially going to be what we just did, except with different data. Okay, is that a 100-able assignment? I think so. Yeah, I think so. There's one more little thing that I want you to do with it, though. Listen very, very carefully. Okay. We will not only learn how to calculate slope via rise over run, we will learn how to get slope on our calculators without having to bother doing the rise over run thing. I'm going to hand out a little instruction sheet for you right now. I'll ask you to take one hand on to the next person. And then I want you to follow along with me on my calculator as I go through the process of getting this slope not by rise over run, but by using my calculator. All right, have a look up here, guys. You see my TID3 up on the board here right now. I want you to make sure your TID3 is on and just clear it, just so it's not so cluttered. And I want you to follow along with that paper that I just gave you, follow along with the calculator up here. First thing I want you to do is click the button Stat. Then I want you to hit Enter, because you're actually hitting Enter for Edit. Right? It's the first option. Okay, right now, I see a blank data table. I want to enter my data into that data table. So let's go my x-axis first. We're going to go 2, enter 4, enter 6, 8, 10, 12, 14, 16, 18, and 20. All my x variables, all my x values, I should say, are in there. Now I'm going to scroll up and do the same thing with my y variables, or my y values. Here we're going to get 12. We're going to get 18. We're going to get 30, 43, 49, 59, 72, 81, 88, and 102. I'll wait for you here until you guys get caught up to where I am, have your data table completed in there. Here's the important part of it now. We've got our data table entered. Now we're going to actually do our statistical analysis on this to find the value of the slope and if there is a y-intercept. I want you to hit Stat again. Stat's the big button. Stat gets entered or hit in order to enter your data. Stat also gets hit in order to analyze your data. This time we're not going to edit though like we did last time, so it's not option 1. This time we're going over to Calc. Okay, that's the middle one. And then we're going to scroll down to option 4, which says linear regression, AX plus B. So that when you're entering the data, it's Stat Edit. When you're analyzing your data, it's Stat Calc, option 4. Once you get there, let's press Enter. Okay, it's just going to tell you what you're doing here. Let's press Enter again. When I do that, you see an equation pops up. It says y is equal to ax plus b. That's what we said yesterday, right? Except we called a, the slope, m. Y is equal to mx plus b. It tells me the value of a is 5.0. And it tells me the value of b is 0.33. So from my calculator, I can see that the slope of the graph, A, is 5. What did I say it was? 4.9. Did I do a pretty good job of drawing my line of best fit and calculating the slope? The actual value is 5. I got 4.9. That's pretty good. I'd mark that right. You get 4.8, 5.1, 5.2. I'd mark that right too. The y-intercept is 0.33. So the y-intercept is basically nothing. It basically goes through the origin. Does that make sense? You can see how practical this is, right? How useful this becomes. We have to be able to calculate slope by hand, but there's times when I'll accept doing it by your calculator as well, because it's a lot quicker. I want you to know how to do it by hand, but if I don't make you do it by hand, then use your calculator, because it goes lightning fast, and as long as you enter everything correctly, you're guaranteed of getting it right. The little mini assignment that's being handed around right now is exactly what we've done here today. It gives you a data table. You need to plot the graph. Make sure you have all the requirements of a graph. Title, even intervals, label your axes, draw the lines on the axes, draw your points, draw a good line of best fit, calculate the slope the old-fashioned way using rise over run, or y2 minus y1 over x2 minus x1. But I also want you to, as you see in the bottom right-hand corner, to do this on your calculator as well. Get the slope on your calculator the way that we just did, and just simply write that number down. Let's see how it compares to the slope that you calculated the old-fashioned way. If you're way off, then go back and recalculate your slope. If you're close, that's good enough.